So let us continue where we left off. Last time we reached to this subject, the floating point. And by floating point, we mean this point. It's a representation for non-integral number. So we have a full representation. We will go through it, and after this we will check the operation, particularly the addition and the multiplication. It's including very small and very large number, but at the start we need to make any number normalized. So as you can see, this number, which is in it's using the floating point, and it is a normalized number, meaning you have a negative or a positive, and then one digit from 0 to 9. After that, you have the point, and you have a fraction times 10 to the power of a certain exponent. And this exponent could be positive or negative. If it's written this way, then this is a normalized number. Now, those two numbers, they are not normalized. And the reason is we don't have a digit here. So the digit over here, it should be from 1 to 9. 0 shouldn't be included. If this was 0 here, then it won't be normalized. It has to be 1, 2, up to 9, and then followed by a period. Here, since we have 0, also 0.00 something, this number is not normalized. Similarly here, we have three digits, and then we have the point. So those two are not normalized. Of course, they can be normalized by shifting operation. Now, in binary, the normalized value should be this way, plus or minus, depends on the sign of the number. 1, this one is inherent. It's in all the representations of all the values. 1 point, and then you have a fraction represented by the x's here. Those digits, either 0 or 1, since this is binary, times 2 to the power. Now in decimal we have 10 to the power. In binary we have 2 to the power of a certain exponent. Now you can see here we have some numbers that are not normalized. They are all binary numbers with integral part and a fraction part, and we have the point in the middle. So what happens here, to normalize this number, we have to move this dot or this point to the left 6 digits. If we move to the left, we are making the integral part, or we are making the integral part have less value. And because of this, we will introduce an exponent, and we will raise it to the power based on the number we shift to the left. And this is what we had. We shifted 6 position. Now the point is here. And we have plus 1 point, and we have a fraction. We have to multiply it by 2 to the power of 6, since we shifted this number to the left by 6 digits. Similarly for this one, this number is negative. That's the only difference here. And we shift this to normalize this number. We have to shift it to the left 2 positions. And you can see this right here. And this is why we multiply it by 2 to the power of 2. So we shifted this point to the left by 2 position, and we multiply by 2 to the power of 2, and now it's normalized. This number here, it has 0 point and some zeros. So to normalize this, we have to move the point to the right. In this case, by 6 position until it's here. You can count them this way: 1, 2, 3, 4, 5, and then 6. So now we multiply it by 2 to the power of minus 6. And the reason is this number have only fraction. And if each time we are shifting to the right, we are increasing the value of this number. So we have to multiply it by 2 to the power of something minus 2 to the power of minus 6. Here we move it to the to the right by 3 positions. And this is why we multiply it by 2 to the power of minus 3. So basically, if you move to the left, you multiply by 2 to a positive power. If you move to the right, you multiply by 2 to the power of a negative number. Now, the floating point standard, it's defined by IEEE 754, and it was introduced in 1985. It's developed in response to divergence of representation. A lot of people represented floating numbers in a different way. So to make it standardized, and this helps making the representation portable in any other device. Now almost it's universally adopted by all the machines. We have 2 representations: single precision, where the floating point number is represented in a 32-bit space. The double precision, you have 64-bit. To understand this better, this is the IEEE floating point format. It has 3 parts: the sign, the exponent, and the fraction. It's also called the mantissa. If you use a single precision, the exponent is going to be 8 bits. And the fraction is going to be 23 bits. Meaning you have 23 bits here in the mantissa or the fraction. And you have 8 bits right there. You can see that in the fraction, it starts from position 0 up to 22. That's 23 bits for the fraction. And here, from 23 to 30, and that's the 8-bit exponent, followed by a single bit for the sign. We have a single bit here, and that's the single precision. 1 plus 8 plus 23 is 32 bits. In the double precision, we have 1 bit for the sign. Now the exponents, instead of 8, we have 11. And for the fraction, instead of 23, we have a long number of bits, or a lot of bits here in the fraction, which is 52 bits. If you add 1 and 11 and 52, you will get 64 bits. Now notice that increasing the number of bits for the exponent, if you increase the number of bits in the exponent, moving from the single to the double precision, you will actually increase the range of the number that can be represented. If you increase the number of bits in the fraction, this means that you are increasing the precision. So the exponent increase the range, increasing the bits in the exponent increases the range, increasing the bits in the fraction increases the precision. Now, this representation, any value would be equal to -1 to the power of the sign. Basically, using this representation, it tells you that if the sign is 1, then the number is negative. If the sign is 0, then the number is non-negative. We said non-negative because it could be positive, and it could be also 0. Now, we have here 1 plus the fraction. So you get the fraction bits and you add an inherited 1. The reason for this inherited 1 is, as we said in the beginning, we represent the binary values as 1 point the fraction. So if you get the fraction bit, you add to it this inherited 1. So it's 1 plus fraction times 2 to the power of the exponent minus the bias. If this is your first time looking at the floating point format, it would be surprising to you, why did they do that? And actually, when at the beginning in 1985, when it was introduced, there was a lot of debate behind this. We will explain some of these things in our slides. Now, here we call this part the normalized significant. So it has a fraction plus 1. So this 1 plus fraction, we call it all together the normalized significant, which means that it's going to be between 1 and 2. If you have the fraction here all zeros, this means you have 1 plus 0, which is 1. So that's the lower bound. If you have the fractions all ones, so that's the maximum number that you can get for the fraction. And if you have everything ones, this means that you could round it and make it another 1. And that would be the upper bound, where 1 plus 1 is equal to 2. Notice that we have an equal sign here, because you can get a fraction that is equal to 0. But here it's strictly less than, because even though the fraction is 1, 1, 1, 1 all the way, it's not actually 1. It's really close to 1. So this means that point 1, 1, 1, 1, 1, 1, 1, 23 bits. This is very close to the 1. Yeah. So always has a leading pre-binary point, which is the 1 bit, the inherited bit 1. So no need to represent it explicitly. And sometimes we call it the hidden bit. The significant is the fraction with the 1 point, which is this part here, restored. Now for the exponent, it has the excess representation, where you have an actual exponent plus a bias to ensure that the exponent is unsigned. And that's the reason we have the exponent minus the bias. And you will see it in the examples after this slide. If you use a single precision, your bias is 127. If you use double precision, your bias is going to be 1023. So you know that this is 2 to the power, this is 2 to the power of 7 minus 1. And you know that this is 2 to the power 10 minus 1. So you can see that the exponent here, we know in the single it's 8 bits. So we take 2 to the power of this 8-bit minus 1, which is 2 to the power of 7 minus 1. Similarly for the double, since we have 11 bits, we will raise it to 2 to the power of n minus 1, which is 11 minus 1. Now we have 10 minus 1. You just, for our course, remember that the single is, the bias is 127 and the double 1023. Here are examples. So you get used to the floating point representation. If you were asked, how is the minus 1.110, that's in binary, times 2 to the power of minus 3 stored in the machine? You would notice that this number is actually already normalized. And this is good. We say the normalized number here is the same number that is in the question, minus 1.110. That's binary times 2 to the power of minus 3. Notice that this representation is following the binary representation that we discussed in the first slide. Here we have the binary number. We allow only zeros and ones, but here it's 2 to the power of minus 3, which is normal decimal system. So it has 2 bars. It's like a mix. Now, since we have a negative number, the sign bits, we need to find actually for the floating point representation, this 3 bars, the sign bit, the exponent bits, and the fraction bits. So first, the sign bit is going to be equal to 1, since we have a negative number. Now for the exponent bits, we check the power of 2, which is here, minus 3, and we add the bias to it. Because we are converting from this number, and we are trying to find the floating point representation. So we say that this is minus 3, and we add the bias. So we are doing the single precession now, and we get 124. The 124 binary representation is this number. And we are following colors here. So if you go back, the sign is the red color, the exponent is the green color, and the fraction is the light blue color. And we are following it also in the example. So that's the sign. Now this is the exponent bits. For the fraction bits, you get the fraction. And luckily, this number is in the normalized form. This one is the hidden one. We don't represent it in the floating point representation. We just take the fraction, which is 0, 1, 1, and 1. You should start from the point and go to the right and start copying the bits, which is the fraction is going to be 1, 1, 0, and the rest of the bits is going to be 0. Remember, if you have any number, let's say decimal number, if we have 9.5, if we added zeros here, you don't change the value. Also, if you added zeros here, you don't change the facts. And this is what we did here. We have those 3 bits here, and we completed the 23 bits of the fractions of the fraction to all zeros, with all zeros. Okay. Now, since we have those already calculated, we just concatenate them. So we have the sign bits, we have the fraction. You always need to make sure that the fraction bit is 8 bits in the single precession. Sometimes, if you calculate the 124, you might reach that the number is 0011111. And that's it. That's the result that you got. Make sure you add this 0 to make the total 8 bits. So now we have the exponent here, and you get the fraction and concatenate it at the end. If you count the number of bits here, you will find them 32 bits, and they are represented in hexadecimal, as you can see here. Now, if you were asked, what is the minus 1.110 in binary times 2 to the power of minus 3 value in decimal? So what happened is, first, we know that this is a normalized form, and we want to find the decimal value. So get rid of this number by shifting the floating point to the left by 3 digits. And that's what we did here, and we got the number here. Now, this is a negative number. So we would say that the number, of course, negative. So we put the minus here. And we got those digits in the fraction. So this one, we multiplied by 2 to the power of minus 1. This one, we multiplied by 2 to the power of minus 2. And this one, we multiplied the 1 by 2 to the power of minus 3. And this one, 2 to the power of minus 4. And this one, we multiplied with 2 to the power of minus 5. And you can notice that those will be cross dots, and you are multiplying by 0. But here, we multiply 1 by 1 over 8, and 1 by 1 over 16, 1 by 1 over 32. And you get the result minus 7 over 32. And if you calculate this, it's going to be 0.21875. So this is the decimal value. Now, if you were asked, and you were giving this number, and you were asked to get the floating point single precision format for that number, what should you do? We put it in the slide by itself. So if you were asked what is the IEEE 754 single precision floating number, representation in the binary for this number, which is the same that we got in the last slide. So what you do is you try to get the binary first. And to do this, you multiply by 2 and you get this number. Notice that this number here is less than 0.5. So for sure, if you multiply it by 2, you won't get a leading one here in the integral part. So you got 0.4375. Now you multiply this again by 2 and you get 0.875. You take this one and you multiply it by 2, and now you have this leading one, 1.75. Now you take the fraction only, which is 0.75, and you multiply it by 2, you get 1.5. And now, at this point, you take the 0.5 only, the fraction, you multiply it by 2, and you get 1. Now, to get the binary number, you start from this one going down. You would say that this number is 0.00111. 00111 times 2 to the power of 0. Or take this out. But we keep it times 2 to the power of 0 because we know that we will normalize it next. Now we know that this number is negative, so we put the negative sign. A few points here. Sometimes you never stop. You keep multiplying by 2 and you never get to 1. You continue forever. If there is a repetition in the numbers that you are calculating, at the first repetition, in the first point, stop if there is a repetition. Even if there is no repetition, for example, if the number is pi, you know that pi doesn't have repetition in the fractions, 3.14, 15, and more bits, or more digits. So if you even multiply it by 2 to get the binary number, you will never stop. So at this point, you know that you want certain digits, so you stop at the digits that you like, or keep doing the multiplication until you cover about 23 bits to fill in the fraction. Don't forget, you will almost normalize, so you might lose some bits or you add some bits. Anyway, for this number, we stopped nicely. So we got the number here. Now we normalize by moving this point to the right 3 times. And this is why we multiply by 2 to the power of minus 3. Now we know that this number is normalized, and we do the same way that we explained in the previous slide. It's negative, so the sign bit is 1. The exponent is minus 3, single precision, so we add the bias 127. We got that 124. We convert it to binary, and we got we got the 8-bit exponent bits. Make sure you add the 0, the most significant. And the fraction bits is the fraction that we got here. So 11000, starting from this part, 11000, and then you fill up with zeros. You can concatenate to get the result in binary, and then you also can get the hexadecimal. Just to make sure you remember, this is going to be B, and this is going to be E, and this one here is going to be 6, followed by 5 zeros. Now, another example, if you were asked to represent minus 0.75 in single per session. Now, another way of getting the binary representation is you say that minus 0.75, you know that it is minus 3 over 4, and the 4 is 2 to the power of 2. So quickly, you change this to 2 to the power of minus 2. And you know that minus the negative sign, you keep it. And the 3 is 1, 1 in binary. So we got the binary quickly. Or you use what we explained in the previous example. You have many of these. Now, in binary, you get this number here, and you know that this is not normalized. You want the floating point to be here. So you know that if there is no floating point, then the point is here. So you need to move it to the left by 1 position. Since this power that we got, minus 2 to the power of minus 1, if we move it to the left by 1 bit, then you need to reduce the power from 2 to the power of minus 2, or increase actually the power from 2 to the power of minus 2 to 2 to the power of minus 1. Now, this number is normalized, so we can get the representation easily. Negative, so we put the sign bit 1. We get the exponent minus 1. We add 127. We get the 126. And you can see that the number is like this. If the exponent here is 2 to the power of 0, then the exponent is going to be 1, 1, 1, 1, 1, 1, 1, 0. And now you see the benefit of the bias 127. So the 127, which is the maximum, is represented this way. So you had the leading 0, meaning that the power is, or this exponent is 127 or 126 and so on. So you have the 127 is the breaking point, and anything lower than that, which will has a 0 followed by 1s. Anything that is more than this, for example, if we got 130, then it will have a 1 right here instead of the 0. Notice that the exponents are unsigned. The exponent representation here, if you see any exponent, so this number can never be negative. It's always positive. But you got it because you could have a negative power here or positive. So you are including this. You just use the bias to ensure that this is unsigned. Now you concatenate and you get the number, and you can also get the result in hexadecimal. You get the 1, you get this one. Oh, the fraction. For the fraction, we have a very simple fraction, which is only this bit. So we got 1 followed by all zeros. And you concatenate, you get the result in binary and hexadecimal. Now, we get more examples. If you got this number where it has integral part and a fraction, so you get the integral part. This number first is negative, so you know that the sign is 1 from the get-go. But also this, it has an integral to 10, and you could convert this to binary this way. Now for the 0.25, you know that the 0.25 is 1 over 4, and the 4 is going to be represented 1 over 4. You know that you need to add 0 times 1 times half plus 1 times 1 over 4, which is going to be 0.01. So now you have the fraction and you have the integral part. So you would say that this is what we got here, and this one what we get here, and the point is between. This is time 2 to the power of 0. It's not in normalized. This is just the binary value, not normalized. To normalize this, you have to move this point to the left 7 times till you reach to this position. And this is why you have 2 to the power of 7. After this, now you know that this is the normalized form. It's negative, you have the sign bit 1. You have 7 in the exponent, you would say 7 plus 127, 134. And now notice that the exponent has 1 in the beginning. If you convert 134 to the binary representation in 8 bits. Now, the fraction bits, we have this fraction. So we copy this fraction right here. And the rest is zeros. And we concatenate. And you get the result. You can also get them in hexadecimal as well. So this example shows you this number, which has integral and a fraction part. Now, if you were asked what number is represented by the single precision float number 0x, I gave you the hexadecimal 0x 00000A0C. So first you convert this to the floating point representation. So C is 0011. The zeros, we have 4 zeros. The A is 0101, and the rest is zeros. Now, you know that this one is the sign, and those 8 bits are the exponent, and the rest is the fraction. Since this is the exponent bit, this exponent bit is 129. The fraction is this fraction. And you could, at this point, plug in the value x that we represented in the beginning. It's -1 to the power of the sign. And you know that the sign here is negative. So you will put 1 here. Now for the exponent, you get the 129. So you get 129 here. And the bias, since this is a single precision, is 127. Now for the fraction part, you have to put its value in decimal. And we get it here in binary. And you know that you multiply this bit by 2 to the power of -1. And this one by 2 to the power of -2. You should include or focus only on the ones. And we have 1 times 2 to the power of -2, which is 1/4 or a quarter, which is 0.25. So we plug in the 0.25, and you can calculate this easily. You can find this part here is 2 to the power of 2, and this one 1.25, and we have a negative number at the end. And 1.25 times 4 is going to be 5. So the number is -5.0. So if you remember, if we use an integer representation for the binary numbers, you know that the -5, if you take, let's say, 32 bits. So you know that the 5 is 101, and the rest are zeros. That's the 5. The -5 is going to be the 2's complement, so you have 1, and then you flip the rest. So 1, 0, and the rest are 1s for the 32 bit. But this is if the number is defined as integer. So remember, if you have a C code or a Java code, and you have defined the number as integer, know that you represent it this way. If you define the number as float in C, then you have the single precision, and your number, this number, the -5.0, is going to be represented, as you can see here. The double, it will be represented using double precision. Now, let's see some examples or some discussions on how to move from single to double precision easily. So in single precision range, you have the exponents, zeros and ones. They are reserved and it can't be used. and we will discuss them next. Now, the smallest value, or the smallest possible value using a single precision, in the exponent, you will have 1 followed by zeros. You can't use zeros, it's reserved for something you will see now. But in the exponent, you have to put 1 and zeros. So the actual exponent here is 1 minus 127, which is going to be minus 126. Now, for the fraction part, you will put all zeros to get the smallest value possible, which is equivalent to the significant being 1. So this number is going to be plus or minus, we're going to both ends, 1.0 times 2 to the power of minus 126. And in decimal, you have it as plus or minus 1.2 times 10 to the power of minus 38. You can plug this in your calculator and you will get this number. So that's the smallest value possible. And you can see here that this power, or even in using power of 2, is very low. It's minus 126. That's the limit of the exponents. Now, if you want to ask about the largest value, then the largest value is going to be, you think it's ones, all ones, but this is reserved. So the next one is 0 followed by 7 ones. So, and the actual exponent is going to be 127. The fraction, you get all fractions bits equal to 1, meaning that the significant is approaching the upper bound of the significant, which is 2. Now this number is going to be plus minus 2 times 2 to the power of the exponent, which is 127. And if you calculate this, you put it in your calculator, you'll get plus or minus 3.4 times 10 to the power of 38. So this is the smallest and the largest value, as you can see. Now we will move to the double precision. And you can try to find the difference between this slide and the next slide. So if you move here, you can see that we are increasing bits in the green, representing the exponents, and in the blue, representing the fraction. Again, this is the single. If you move to the double, then you can check that there is an increase in the bits. And we know this because the exponent in the double precision is 11 bits. And this is the smallest value of the exponent, meaning it's going to be minus 1022. And the fraction is, in the fraction you have 52 zeros. And this is equivalent to the lower bound of the significant, which is 1. Now moving to the largest value, the exponent, you can see that it's kind of the ones complement of this one. So you have 0 and 1s, and the actual exponent for this one, now you subtract from 1023 since we are using double precision, and you will get 1023 as the result. And the fraction part, you will reach to the upper bound, similar to the single precision, which is 2. Now, applying this, the smallest value is going to be plus minus 1 times 2 to the power of minus 1022. So now you have more precision. And plus or minus 2.2 times 10, which is going to be plus or minus 2.2 times 10 to the minus 308. So if you check this number and compare the double to the single, compare this one to the single, and you see that this is the 38, while this one is 308. Now, the largest value is going to be plus or minus 2 times 2 to the power of 1023, which is, if you plug this in your calculators, would be plus or minus 1.8 times 10 to the power of 308. Now, what about the floating point precision? Now, it's a relative precision. All fraction bits are significant. So we care about the fraction here, which is the mantissa. In the single, it's going to be 23 bits. In the double, it's going to be 52 bits. Now, in single, this precision is 2 to the power of minus 23, approximately. Because you are using in binary 23 bits for the fraction. Now, if you convert this somehow to decimal, you will have 6 digits. How we get this? We multiply the 23 times log 2 to the base 10. And this is equal to 23 times, this value is about 0.3. 23 is times 0.3, have 6 decimal digits of precision. If you calculate this in your calculator, you will find you that you have 0.00. So the precision here have 6 decimal digits. Now, if you do this for the double, you have 52 bits, and you do the same here, but now you're multiplying by 52, you will have 16 decimal digits. 16 decimal digits. Now, we will see the other numbers that we just talked about. Remember that we said the exponents, zeros, all ones, they are reserved. Reserved for what? The first one, when the exponent is zeros and the fraction is also zeros. At this point, you will notice that the fraction here is 0. And the exponent that we put here is also 0. Now we will allow the hidden one that was here to be also 0, to make this number where the exponent is 0 and the fraction is always also 0, representing plus or minus the value 0.0. So now the 0 we have plus, and we also have a minus 0 in the floating point representation. So in summary, if you have the exponent zeros and the fraction also zeros, then you are having plus or minus 0 in the result of the floating point representation. Now, what if the fraction is not zeros? So now you will have this value and you have a fraction that is non-zero. So at this point, what you are doing is you are getting a d-normal number. We said they are d-normal because you don't have the leading one. That is 1 point. We have 0 points. So we call them denormalized number, and we allow them to represent smaller than normal numbers, which makes it easier for us to get gradual underflow with diminishing precision. So those small, tiny numbers, you can represent them by having the exponents zeros, and you get a fraction. The lowest number that you could get is 1, 0, 0, 0s, 23 times. Now, what about if the exponent is 1? Now we have two cases similar to the previous slide. If the fraction is 0, if the fraction is not 0. Now, if the fraction is 0, we will consider this plus or minus infinity. That could be used for subsequent calculation, avoiding the need for overflow check. So it's like you have a saturation point. Anything that has the exponent all ones and the fraction zeros, then you are reaching plus or minus infinity, depending on the sign bit. For this one, where the exponent is ones, and the fraction not equal to 0, then this is not a number or NaN. And some calculator, when you do like calculation that represents the floating point this way, you get this in the LCD of the calculator. This indicates that this is illegal or you have an undefined result. For example, if you divide by 0 or you have 0 divided by 0. Now we got all the cases listed in this table. The smallest value, you will get the fraction zeros, and the exponent for the single would be 1 followed by 7 zeros, but for the double, 1 followed by 10 zeros. The largest, you will have the fraction all ones. For the single, the exponent is going to be 0 followed by 7 1 and 0 followed by 10 ones for the double. Now, if you have the fraction equal to 0 and the exponent also equal to 0, then this is the plus or minus 0 based on the sign bit. If you have the exponents 0, but the fraction is not equal to 0, then this is a denormal number that we allowed to have this diminishing behavior where we could represent a very small numbers in the positive or the negative side based on the sign. And we check this in the slide that we talked about it right here. Remember, now we are allowing the 0 here. Now, if you have the fraction zeros and the exponent all ones, then this is plus or minus infinity. If you have the exponents all ones, but the fraction is not 0, then this is not a number. Any other that is not of these cases, this is a normal floating point number where the fraction could be anything, and the single you have from 1 to the maximum, which is 255, since you have 8 bits, and for the double you have from 1 to 2047, since you have 11 bits in the exponent. At this point, we know the floating point representation, and we give you a lot of exercises about it, and we also check different scenarios where we have numbers like plus minus infinity, plus minus 0, denormalized numbers, and others. At this point, we will go to the operations or the arithmetic of the floating point. We will only discuss the addition and the multiplication. So for the addition, let's consider a 4-digit decimal example where you want to add those two numbers. So you do at the beginning, what you do those 4 steps. At the beginning, you need to align the decimal points. You align this point. How? You shift the number with the smaller exponent. So you see the exponent here and here, and you found out that this is the number with the smaller exponent. So you need to shift this one. You move this point to the left 2 times to increase the power to 10 to the power of 1. So you need to move 1 time to make it 10 to the power of 0, and another time to make it 10 to the power of 1. And this is what we did. We moved it 2 positions. So we added 0 here and becomes 0.016. Now, after the alignment and making sure that the exponents are the same, and this is the rule that we decided on, that we shift the number with the smaller exponent. You could shift the number with the larger exponent. The goal is to have the same exponents and to unify their procedure and also the hardware. We always shift the number with the smaller exponent. After this, you are ready to add the significand. The result will have the same exponent. And you add those 2 numbers, and you can see this is the result of the addition. Now, when you get the result, there is a strong chance that you won't have a normalized number in the result. So what you do next is you need to normalize the result and check for the over and under flow. We normalize it by moving this point or decimal point right here. And we make now the power, instead of 10 to the power of 1, it's going to be 10 to the power of 2. Now, if you have a specific number of digits in the fraction, here we consider only 3 digits, then you need to round and renormalize if this is necessary. At this point, we have 4 digits, and we don't allow 4 in the fraction, we allow only 3. So we make it, instead, you know that we have a 5 here, and you should round it to the next digit, and the 1 becomes 2. Now this is for the decimal. For the binary, we have the same steps. Now consider these two numbers. Now they are in their normalized form, and you want to add them. This one is in its normalized form, this one also in its normalized form. Now to add, first you shift the number with the smaller exponent. This is the smaller exponent, so you shift the number to make this exponent 2 to the power of minus 1 by moving the digit this way to the left. And that's what we get here. After this, you know that the power in the result is the same, since you aligned the numbers. And you can add. Notice that this number is positive, and this number is negative. So this addition is actually a subtraction. And you know that subtracting 1.000 from 0.111, you will lift up with only 100.0. Also, you could do it this way. You would say that this, I want to subtract this number from this number. Don't worry about the point for now. So to subtract, you convert it to addition by having this first operand the same. The second operand is the 2's complement. And you add. If you add, you'll get 1 here, you'll get 0 here, and you'll get 0 here. And here you'll get 1 plus 1, that's 0, carry 1, and you drop this carry out. So the result is going to be 1, 0, 0, 0. Since you have the point here in the addition, then at the result, you'll have also the point right here, as you can see. Now, after getting this number, clearly this is not normalized. So you need to normalize it by moving this floating point to the right 3 times. So 2 to the power of minus 1 becomes 2 to the power of minus 4. Now in binary, it's very easy to check for the underflow and overflow. Because this exponent, you check if it is between minus 126 and 127, then there is no overflow or underflow. And this is usually the case. IEEE standards was represented, taking into account that we make the overflow or the underflow a rare case. So here, this is minus 4, and it's following, or it's between the lower bound and the upper bound. So there is no overflow. At this point, you round and renormalize if this is necessary. Now here we didn't do any. It's the same. There is no change. Because remember, in the fraction, we have up to 23 bits. So only if after the addition, we end up with 24 bits or more, then at this point, you do the rounding and renormalizing if it is necessary. Now, this is a simple example. This is also another example. If you were asked to add the decimal numbers, this number and this number, using the binary float point addition. So what we did at the beginning, and this is a good exercise for you, you need to represent this number, which is in decimal, to binary. Similarly, for this number, you generate from the decimal its binary value, which is the normalized form. Now you do the addition, you notice at the first step, the exponents are different. So you shift the number with the smaller exponent. So you need to shift this number. This is the smaller exponent. And to shift it, you need to move it to the left. If you move it 2 times, you will have 2 to the power of 0. Then you need to move it 4 more times to get 2 to the power of 4. So you need to move this point 6 times. So you moved it this way: 1, 2, 3, 4, 5, and 6. So now you can do the addition, and we will do it the same way that I just explained. 0 plus 0 is 0. 0 here, 0 here, 1 here, 0 here, 0 here, 1 here, 0 here, 1 here, 0 here. Now here 1 plus 1 is 0, carry 1. 1 plus 0 plus 1 is 0, carry 1. And this one will be down here. 0 plus 0 is 0. And here you'll have 1, you'll have 0 here, and you'll have also 1 here. And 1 plus 0 is 1. Now you get this form. Now, luckily, after the addition, we got also the result normalized. So you don't do this step. You just copy the result again and check for the overflow. We have 4 between the upper and lower bounds, so there is no overflow. After this, remember we have up to 23 bits. And here, if you count the number of bits, surely they are less than 23. So you don't do anything in this step, you just copy it the same. And now you know that this number is positive. Remember at the beginning, this number is positive and this number is also positive. So the result is positive. So the sign bit is 0. The exponent bits, we have 4. So 4 plus 127 is 131. And 131 is represented 2's or the binary this way. The fraction bit, we have this fraction. Now it's a little bit long, so it's fine. We have up to the 23 bits. And we keep copying, starting from this bit, going down. We copy it this way. And the rest of the bits is going to be, when we copy this fraction, we copy it this way, here, and the rest of the bits here, we filled it with zeros. Now we concatenate to get the result. So the addition of those two numbers is represented in hexadecimal this way. Now, this is also a good exercise for you. You can add those numbers in decimal fairly easy. And you can get the result, 26.54004. Now your job is, if you have this number in decimal, how to get the floating point representation. So check if you can get the same floating point representation. Now, at this point, we will check the floating point adder hardware. It's much more complex than the integer adder, and you'll see this in the next slide. Doing this in one clock cycle would take too long. It's much longer than the integer operation for sure. The slower clock would penalize all instructions if you do this, even the instruction that doesn't have to do with anything related to the floating point, because this hardware will be part of your system. And sometimes you need to go through this long hardware, complex hardware to get some result that's not directly related to the floating point. The floating point adder usually takes several clock cycles, but it could be pipelined, and this idea is very important, and we will talk about it in detail when we talk about the processor and the next chapter. Now, this is the hardware for the floating point adder. You can see from the beginning that this is the first number represented in the floating point representation, sign, exponent, and fraction. This is the other number, and this is the result of the addition. You can see it at the end. Also, by looking at this, you notice that you have a control unit that controls many registers, and this register, this register, this register, and this one here, and also control the multiplexer. This also designed by finite state machine, and it is considered as a sequential circuit. Other than that, you have a big ALU and a small ALU. Now, what we are trying to do is the 4 steps that we just discussed for the addition. So at the beginning, we compare the exponent and shift the smaller number to the right. And this is why we have those 2 muxes. And we have also this small ALU. This small ALU will take the exponent here and the exponent here and subtract them. And from that, you can get the exponent difference. And from this, you know which one of them is less than the other. This will be one of the inputs of the control to control those 2 muxes. Because one number will go here normally, and the other one will go here after you do the shifting to the right by the right number of bits. Because this is what we do in step 1. We compare the exponent and then shift the smaller number to the right. Now notice this multiplexer, either it has this fraction here, it also go here. Similarly, this fraction go here, also it goes here. Meaning we will choose one of them normally without change, which is the one with the bigger exponent. The other one, it depends, maybe it's this one, maybe it's this one. It's based on the mux, the result of the mux. But surely the result here is going to be the smaller number, or the number that has the smaller exponent. So notice now that this adder is dealing with the exponents, while this big ALU is dealing with the fraction. And this is what we did in the addition. If you made sure that the exponents are aligned by shifting the small number to the right, based on the difference, you get the correct number of the shifts. What you do for the addition, you add the fractions. And this is what we did here. Now, after you get the result, you have to do step 3 and 4. Where in 3, you need to normalize. So based on the number that you get here, notice that it's fed back to the control because you need to make a decision. Then you would take the number and shift it to the left or to the right based on the normalizing step. And while you are shifting to the left or the right, you either increment or decrement the exponent. And this is why we have a multiplexer here that's getting the result of the exponent. Notice that this is coming from the exponent of one of the variable, either this one or this one, and you should choose the one that you did not shift. which is the one with the maximum value. So after you do this, you finished step 3, and the last step, you get the rounding hardware in case the fraction is or having more than 23 bits in the single precision, or more than 52 bits in the double precision to get the result. So as you can see, this control or this hardware is fairly complex to do just the addition. Compared to the integers, you just need full adder. And if you, for example, have 32 bits, then you could use ripple addition, where you have a full adder repeated 32 times, and that's it. Now, we will move to the multiplication. The decimal floating point multiplication, if we take those numbers, those are decimal now, and you want to multiply this number by this number. Now you don't have to worry about aligning the exponents. You actually add them. So for a biased exponent, you subtract the bias from the sum, or you simply add this exponent to this exponent, which is 10 plus minus 5, which is equal to 5. So now you're done with the exponent. Now for the significant, which is this number and this number, you do the multiplication this way. Now I did the multiplication without considering the points, and I will tell you what to do at the end. Now if you multiply, we have a lot of zeros, and 0 makes multiplication easy. 0 times this number is 0. 0 times this number is 0. 2 times this number is 2,220, and 9 times this number is 9,990, and then you add. This is 0. Here you have 0. Here you have 0. Now here you have 2. 2 plus 9 is 11. So I have 1 and 1. And 9 and 2 and 1. This is 12. So now you have 10 at the end. Now we got this number. You notice that there is 3 bits or 3 digits in the fraction and 3 digits in the fraction. So the total is 6, and you move the point 6 times. 1, 2, 3, 4, 5, and 6. And you get the result, as you can see here, which is this one. And we already finished with the exponent, and we know it's 10 to the power of 5. Now, you know that this is not normalized, so you need to move this point right there. And this is what we did here. Since we are making the value of the number lower, we need to increase the exponent from 5 to 6. Now you round and renormalize if necessary. It's not in our case, except that if we make this condition that we only allow 3 digits. So at this point, you allow 3 digits. So we have 4. So you take out this 2. And this is what we do in the round. Now at the end, and this is the last step. Remember, in the addition, we have 4 steps. In the multiplication, we have 5 steps, because at the end, we need to determine the sign. This is a positive number multiplied by a positive number, so the result would be positive. And I think you know, if you have a negative number multiplied by a negative number, then also the result is going to be positive. If you have different signs, one of them is positive and the other is negative, then the result is going to be negative. Now for the binary, we follow the same scenario. We have this number, and we want to multiply it by this number. Well, these are the decimal values for them. Notice one of them is positive and the other one is negative. So the sign at the end must be negative. Now for the exponent, you add them. You simply add them. -1 and -2 is -3. This is the unbiased exponent, or you could use the bias. I don't recommend it, but just so you know, this exponent is equivalent to -1 plus 27, and the next one is -2 plus 27. So you represent them here while they are biased in biased form, and you subtract from them one of these 127. And to do this, or when you do this, you notice that you will have -3 plus 254 minus 127, and this would be -3 plus 127, or you could simply take this out with this one, and you end up with -3 plus 127, and this is going to be 124. But you could have got this easily from the unbiased, because the unbiased, you just add the exponents, and you get -3. You know that this is unbiased. So to make it biased, you add the 127 to make it 124, and that's it. After you've finished with the exponent, you multiply the significant. We had this significant and this significant, and you multiply them together. Notice that we take the whole number. This is the significant. It's not only the fraction. We take the whole significant. So you multiply those together. And this is what I did here. And I took out the floating point. And I did the multiplication. And you can do it, and you find out that this is the result. After you're done, you add the decimal point by knowing that there are 3 and 3 bits in the fractions, so the total is 6, and you move 6 position, 1, 2, 3, 4, 5, and 6, and you get 1.11 followed by those zeros. And this is what's the result that we got here. And luckily, this result is normalized. So we keep the same number. We take out the zeros, but if you kept them, this is okay, even if you kept the zeros. There is no overflow. This is between the lower bound and the upper bound. You don't need to do rounding. And at the end, you determine the sign. And we even did that from the beginning, because we know that this is positive and this is negative. So you add the sign, and now you have the multiplication. And if you want this result to be represented in floating point representation, you can do that. And we have example like this one in a previous slide. I also added this example for your practice. This is a decimal number multiplied by this decimal number. This is its binary representation. You can practice finding this number. This is the floating point binary representation for the other number. Now we add the exponent, -4 minus 1. This is -5. We're done with the exponent. Make it easy for yourself this way. The second stage is multiplying the significant. These are the significant. So you multiply this one by this one. And we know the exponent is 2 to the power of -5, but we don't take this into the multiplication. We take only the significance. And I got them here without the point. I did the multiplication, and this is what I have. And then I moved 6 positions, since we have 3 to get the result. And I got the result this way. And this is the exponent. And you can see here that it's not normalized. I need to move this point here. And this is what I did here. And by lowering the value of the number, we need to increase the exponent from 2 to the power of -5 to 2 to the power of -4, because I moved only one position. And this is falling between the bounds. There is no overflow. And I didn't need to do any rounding. And notice that all the exercises that I'm having, I don't do the rounding, because I have only a number of bits in the significance. Otherwise, we will have a very long multiplication with many partial products. Now we got the result this way. And we also can determine the sign, and you can see that this is a positive number. This is also a positive number, so the result is going to be positive, and this is why the sign bit is going to be 0. The exponent, it's -4, so I added 127, and the result is 123, represented an 8-bit this way. The fraction bits are those bits. I copied them here, and I filled with 0. And I concatenate the red, this is the sign, the green, which is the exponent, the blue, which is the fraction this way. And I got the results, both results, and I also represent them in hexadecimal. You could find that if you have this number and you multiply it by this number using your calculator, you will get this result. Try to, from this result, or from this number, try to do the floating point representation yourself, and you should be able to get the same representation. Now, at this point, for the floating point multiplication hardware, the floating point multiplier is of similar complexity to the adder. And you can notice that the only difference here is that we are adding the exponent instead of aligning. So it's very close to the adder, but uses a multiplier for significant instead of an adder. The floating point arithmetic hardware usually does the addition, the subtraction, the multiplication, the division, the reciprocal, the square root, and many other functionalities actually. What we covered here is the addition and the subtraction too, and also the multiplication. There is another way of doing this, and to understand it better or having those also functions, you should study a master course in computer arithmetics. The operation usually takes several clock cycles, and this is obvious, and it also could be pipelines to make it faster. Now, the floating point instruction in MIPS, we have actually a floating point hardware, which is coprocessor 1. It's a adjunct processor that extends the ISA. So we have a main processor, and we also have a coprocessor, which is coprocessor 1. This coprocessor is only for the floating point arithmetics. It has a separate floating point register. It has 32 single precision registers from F0 to F31, and you need to pair two together to make a double precision. So you will take 0 and 1 as a one register, which has 64 bits for a double precision. Release 2 of the MIPS ISA support 32 64 floating point registers instead of only these numbers, because here if you have 32 single precision registers and you pair each two together to get the double precision, then you would have 16 64-bit double precision registers. And in the release 2, they made those 16 32 registers. Now the floating point instruction operates only on floating point registers. They don't take the T register or the S registers. They had to take the F registers. Programs generally don't do integer operations with the floating point data or vice versa. More registers with minimal code size impact. And if you want to check this point, there is some explanation in your textbooks. The floating point load and store instructions are these instructions, and you read them this way. Load word from coprocessor 1. Notice that you have coprocessor 1 in all these instructions. So either you load or you store, or this load and store for a word, meaning that you are dealing with a 32-bit. Load double and store double, this is for the double precision registers. This is an example instruction where you load a double data from coprocessor 1, where you have the stack pointer and offset 32, so you load into register F8, meaning that the result, which is going to be double now, so it's going to be 64, will be saved or will be read from the memory and saved in register F8 and F9, since it's double. Here are some floating point instructions in MIPS. A single precision arithmetic. You have add, subtract, multiply, division, but you have .s indicating that this is a single precision operation, and this is an example. Notice that you are using now the floating point registers. The double precision, you'll have the same, but instead of .s, you'll have .d. This is the multiplication, for example, multiplication, .d, and you have the F registers, as you can see. Now, for a single and double precision comparison, now the comparison instructions, you have this instruction, c.xx.s, c.xx.d, C for comparison. So you are trying to compare, is this equal or less than or large or equal, something like this. So you compare this number. If you have .s, this is single precision. If you have .d, then this is a double precision. So what happens here in XX, it could be equal, could be less than, it could be less than or equal, and there are many versions. This is an example, one of them. If you have C, so you are comparing, it tells the assembler right away that this is a comparison instruction in the floating point. You are doing less than, so you're checking if this is less than this in single precision. Branch on floating point condition code, it has this format. You can see that this is branch, PE for branch, and you have C1 here for coprocessor 1, and this is an example. You can branch for coprocessor 1, meaning that you are using the coprocessor now, and you are doing or going to this target label. Notice that here you branch only if the condition code of the floating point operation true or false. That's it. So that's why you have branch for true and another branch for false. So branch on coprocessor 1. If the condition code is true, then you go and branch. Otherwise, you don't. And you branch to this target label, whatever it is. So you know that there is many instructions related to their floating point. For the accurate arithmetic, the IEEE standard 754 specify additional rounding control. So let's say you have single precision and the fraction is more than 23 bits. So you have extra bits of precisions, 3 bits, guard and round and sticky bits. Those 3 bits make many choice of rounding modes and also allow the programming to fine-tune the numerical behavior of computation and rounding. And I suggest you read what your textbooks said about those 3 bits. What's the job of the guard bit? What's the job of the round bit? And what's the job of the sticky bit. Note that all floating point units implements all options. Most programming languages and floating point library just use the default way. The trade-off between hardware complexity, performance, and market requirements make the choice actually. So if you don't worry about the details, you will get a cheaper floating point coprocessor, but it doesn't have all the features. At the end, we will revisit or introduce some of the fallacies and the pitfalls, so be aware of them. For example, the right shift and the division. You know that the left shift by I places multiplies an integer by 2 to the power of 5. But you might think that this is the same behavior. If you do the right shift, then you will divide by the integer, or you will divide this integer by 2 to the power of 5. And that's not true. And the reason is, as you can see here, the right shift isn't going to divide by 2 to the power of I. This is true only for inside integers, for unsigned integers. For signed integers, it doesn't work. You have to be aware of how the shift happens. So if you use arithmetic right shift, meaning you have -5, for example, and you want to divide it by 4. If you shift to the right by 2 positions, indicating that you are dividing by 4, what you are replicating is the sign. So this one would be here. And then you will drop those 2 bits because you are shifting to the right. But the result now is -2, meaning you are dividing -5 divided by 4, which will be 2 or it's not going to be -2. -5 divided by 4, you know that it's not -2. So basically, don't use the right shift for division. If you do the logical right shift, you will replicate zeros. If it is logical shift, not the arithmetic. And you do this by, instead of having the ones here, you will add zeros, and this will be even worse. If you do the division here, it's going to be positive 62, which is absolutely incorrect. And this is why you shouldn't do the right shift for division, and that's one of the fallacies. Now, the associativity. That's another fallacy here. You think that if you have 3 operands represented in floating points, and you add x plus y, and then you added z, or you added y plus z, and then you add the result to x, you will get the same result. But that's not the case. You have to be careful, especially if you are a developer or a hardware engineer trying to implement the addition. You have to be aware of the associativity. Let's say x is this value, which is negative with a big power, as you can see here. Let's say also it's a single precision, represented in single precision. Let's take y and make it positive. It's the same value, but instead of negative, it's positive. And we have z only 1.0. If you add x and y first, so you know that this addition will cancel each other, and you will get 0.00 times 10 to the power of 00, which is actually 0. And then you add z to it, which is 1, and you will get result 1.00 times 10 to the power of 00. Now, if you do the other way around, where you add y plus z, so if you add the y plus z, this is actually reaching to the limit in the single precision. So adding to this huge big number only 1 doesn't change the value. because this is a huge number and this one. So if you add 1 to it, the hardware will do the rounding, and because of the rounding, it will take this one out and it would be the same as y. And now if you add those two, you will get 0. They will cancel each other and you will get 0. And there is a difference here. The result here is 1 and the result here is 0 because of the rounding. So you need to be aware of this problem regarding the associativity. Now, who cares about the floating point accuracy? There was a historic debate about this. It's some people, they say that it's only important for scientific codes and nobody cares about this. It's only scientific or mathematician or professors and not the normal users. But for everyday consumer, let's say this example, like your bank balance is out by 0.0002 cents. So as you can see that you say, this is not much. And probably if this is in your bank account, you won't worry much. But you know that in history, some people can accumulate this number from many, many users and get a good amount of money. So this is important when we talk about money, that to be accurate when you talk about the floating point. And there is also a historic bug, which is called the Intel Pentium from Intel company, Intel Pentium, the floating point division bug. If you want to read about what happens, it has a long story. See this reference. The conclusion of this story that the market, even the normal people, expect accuracy. And because of this, at the end of the story, Intel published an apology, and they say our current processor, which is Intel Pentium, having a bug. If you bring it back as a recall, we will give you the new version. But many analysts estimated that the recall cost for Intel is 500 million at that time when they introduced the Intel Pentium. If my memory served me well, I think it was in 1994 or 1995. Though it cost to fix this bug 500 million. As a conclusion, concluding remarks, the bits have no inherent meaning, and you can see sometimes we use 32-bit to represent numbers, to represent instruction, to represent those numbers as integers, to represent them at float, to represent them at double. So the interpretation depends on the instruction that is applied and how you break it down. The computer representation of numbers, they have finite range and they have certain precision. So be aware of the roundings. You need to account for this in your programs. The major difference between computer numbers and the numbers in the real world is that the computer numbers have limited size and limited precision. It's possible to calculate a number too big or too small to be represented. If you are trying to get a diameter of a really far away star, you might need a really big number to be represented, and even the 64-bit is not enough. So be aware of your application. The programmers must remember these limits and write the programs according to these limits. They either support arithmetic, signed and unsigned integers. So we study the integers and we know how. The floating point approximation to real world numbers, and we did study the floating point. And I hope you understand how to do that. You have a bounded range and precision again. So you need to check for the overflow and the underflow. What's the upper bound? What's the lower bound? And the MIPS ISA, as a conclusion, the core instructions, you have 54 most frequently used instructions of the MIPS ISA. From the long list of different instructions, you have only 54 most frequently used. This is accounting for 100% of the SPIC integer benchmarks and 97% of the SPIC floating point benchmarks. This means that the MIPS ISA is really good. It's covering the integer completely and really high percentage of the floating points when you are doing the benchmarking. Other instructions are less frequent, but they are there for if you needed to use them. And it's good to say that in the next chapter, when we develop the processor, we will take only a subset of those most frequently used instruction, and based on these, we will build our hardware of the processor.